Hello, Mr. Ryan. How are you today?
Good.
Okay, so we may use this bisect package before, yeah? Bisect. What does it mean?
By sharp.
Bisect.
By sharp.
So it's a package.
Jennifer.
So usually we say from bisect, we can import two functions. Import two functions, which is bisect left and bisect right. Okay, we're going to talk about this today. Bisect, binary search, binary. Yeah. Remember, if we have a sorted array, right? Sorted array, 1, 2, 3, 4, 5, blah blah blah. If it's the sorted, if this array, a list is sorted, we can find element which is if it's in the array, which is pretty fast, right? Yeah.
Mm-hmm.
And the time complexity, if that n element is you should know this. If that n log, if it's sorted,
log n.
yeah, log n. Because every time we can do this binary search, yeah, half, yeah. But if it's not sorted, we need O and log n to sort it, yeah. This is sorting algorithm. And if we do this linear search, like if we are performing the search, checking linear. If we're doing this linear search from the beginning to the end, yeah, 1, 2, 3, and the time complexity will be what? In the worst case, if we're going through each element one by one, what's the time complexity? Anyone? You know? The worst case. This is to be easy. What?
O-N.
Yeah, because in the worst case, you need to check n elements. Oh, okay, that's pretty basic. So bisect. Okay, so if I have a array, sorted array like 1, 2, 2, 3, 3, 3, 4, 5. Okay. So bisect left and bisect right returns the insertion position. Okay.
So bisect left is 1, 2, 2, and bisect right is 4, 5.
Bisect. If bisect left, if this is array, the first parameter is the list. So we give a list, and the second parameter is the number, the x, yeah. So you can say x equals, let's say 3. So you will return a position, right? So you will return here, right? So you will return a position, insertion point. You will return an insertion point. Insertion. What's insertion? Insertion point I, right? So A up to I for E in. So any elements in up to I element I is all smaller than what? Than x. Smaller than x. Right? So I insert. So the insertion point will be here because all the elements up to these 3. Look here. It's all smaller than 3. Right? And all the elements at I from index I upwards is all bigger or equal x. Okay? And then the opposite, bisect right. A3. Okay, so it's different. It will be returning the insertion point here. Right? Alright? So what does it mean? Here it's quite similar, except that E in AI and E is smaller or equal x, right? So all these is smaller or equal to x because I pass 3 here, so all these are smaller or equal to x. And all the elements start from I is bigger than x. Okay? Make sense? So do this, and I'm going to test it, give you a small test.
Oh.
Yeah, what? Okay?
What is
What?
E?
E in. So every element up to this insertion point will be smaller.
What question are you going to give?
I'm going to give another one. So maybe this one, and I'm going to change this to 2. So you tell me what's the insertion of the left and what's the insertion of right.
I don't understand what's the bisect left and bisect right.
So I'm just explaining here. So bisect left returns insertion point. So we're going to put the element 3 in this sorted array.
To the left.
So if I have a 3 here, right? And I put it here, so to all the elements, so the new 3 will be here, right?
But it's already 3.
I know, but okay, so I can put.
Yeah, but why is it there?
Why is it there? What do you mean?
But
So this is the new insertion point. You don't get it?
Then why does the 3 go down?
That will be returning, that's what I'm saying. That will return the insertion point I, where to put the new element x. This is x equals 3. So you need to put it here, right? Because all the elements up to this point are smaller than the x, right? Because all the elements.
So it needs to be bigger.
Yeah.
So
yeah. But this right is slightly different. Is that you need the insertion point left.
The same, but is at the right.
Yeah. Okay. So let's.
Just the same, but just at the right side.
Yeah. Most likely. So because this is smaller or equal x, and this is smaller than x, right? Because I put a 3. In all the left, to the left, everything to the left of the insertion point needs to be strictly smaller. But by set right, it's all the elements on the left hand side, yeah? This one, yeah? Look, it's smaller or equal to, right? Got it? Okay?
Yeah.
So if I have 2 here, by set left 2, where do you think you're going to be? Can you point to me?
Here.
Here or here? Come on, by set left. 2, if it's 2. Where? Yeah, this one too. And if it's by set right 2, where is it going to be? Here. Right? Because all the elements needs to, yeah? Got it? It's the same as 3, okay? Go back.
I got 1 correct and Ryan got 1 correct.
Okay, that's fine. But you understand, yeah? There's a slight difference between these two.
And I got 1 wrong and Ryan got 1 wrong.
Okay.
There.
Okay, so how about if this is, we can implement this using linear search, yeah? Look. Look. So how can we implement this? Let's implement by set left using the linear search. Okay. Let's just quickly write it. Define by set left. Sometimes by set is equals to by set left. Okay. X. Okay. By default, it has 2 parameters by default. X equal, it has the lower index equals 0, right? By default parameter. And the high equals none. If high is none, then high is the length of the A. Yeah. So we can just do this for what? For I in range
10.
length A, right? Then we can say if AI, right? If AI.
AI is a robot.
If AI is, look at, on the by set left is strictly smaller than x, right? So if AI, okay, 1, 2, 2, 3, 4, 5. So by set left 2, by set left 3, it will give me here, right? So if this element is what? By set left. Okay, I'm a little. So look, by set left, yeah. By set left is here. By set right, 3 is here, right? So the left, if 3 is bigger or equal, right? It's bigger. It should be bigger or equal, right? X, then we return I. Am I right? Make sense? And otherwise, I will return the first one, right? Return if what happen if there's this element is 100, right? If this element x is 100, and then the first element to add is at the end, right? If the element is 0, okay, so this element is bigger than that, then bigger or equal. It's bigger or equal, then I return I, right? So let's give an example. Like if I want to input x equals 0, look at me, 0. AI 1 is bigger or equal than 0, so I return here. That's correct. How about 1? 1 is bigger or less, I return here. Correct. If it's 2, 1 is smaller than 2, no? And then 2 is bigger or equal than 2. So always I return that, right? So that's correct. So otherwise I return the length of A. Right? Alright? So what's the time complexity if you look at this one?
Oh,
we're going from the start to the end. What's the time complexity? Right? We are not using the advantage of we are not getting this advantage of using this sorted, right? So we are not using that.
Why?
Good question, and that's what I'm going to do next. Okay, so look at bicep right. So for example, for bicep right, so this one needs to be, so we just have to change this equal to bigger, right? So if it's equal, then I keep going, right? And then if it's bigger, look, 4 is bigger than 3, then that's the insertion point, right? So the difference between bicep left and bicep right, if it's a linear search, the difference is just this sign, right? Because all the bicep left is everything needs to strictly smaller than x, right? Bicep right is not, because we have this equal sign. And as we said, this is the slope because we're not using this fact that the array is sorted.
Why?
Good question. Then I'm going to implement this. Okay. Okay, let's implement this.
Ta-da!
Define bicep
I have a bow.
left. A x low equals 0, high equals none. Okay, then let's do this. Okay, first of all, if low is smaller than 0, yeah, we can support it, then we can just raise value error or whatever exception, yeah, value error. Okay, you can put a custom error message here, right? This is for computer to scream that, okay, you give me a value low which is negative, which I can't handle. I'm not happy. Raise exception. Or simply assert, it's quite similar, okay? Then look, if high is none, then high will be equal to length of the A, right? Length of A. Now we can say while low smaller than high, right? What mid? How do I get the middle if I have a lower and half upper?
Lower from upper.
Divided by 2, right?
Hey.
Okay, everyone, come on. So look, and then now look, if I check the middle, yeah, if A mid is smaller than x, if the middle one is smaller than x,
Whoa.
then what should we do? If the middle one is smaller than x, then where is it going to be? If the middle one is smaller than x, what's it going to be? Look, this is mid here, because it's sorted, right? Low, this is high.
Your leg is my head.
Look, if the middle one, if the middle one,
low.
yeah, low. If the middle one,
How do you spell low? Look.
if the middle one is small, if the element middle one is smaller than the element we're looking for, so which half is going to be? Where's the element going to be? It's in which side?
The left.
No. Look. If the middle one is the smaller than what are we looking on the right? Yeah. So okay. So then we say what? So we move it to the right. Low equals mid plus 1, right?
That's not how you spell low.
Here. Okay, that's fine. As if on the left side, so we can say what? High equals mid, right? And then at the end, we just return low, right? Return low.
Return.
Okay.
Not now, we spell low. Return.
Shorter is better, okay? Shorter is better.
Yeah, but they'll say return low.
Okay, let me just check a little bit. Yeah, return low.
Lol.
Okay, low.
Lol.
Okay, so actually, because the parameter is low, okay? Right?
Lol.
Sometimes, look, remember, sometimes there's another actual parameter which default is key. So you can specify how to compute the key. So you can put a key here, right? And if key is not empty, you can just say key, like calling the key function. Yeah. Sometimes you can pass the customer key function in there. What's the time complexity for this one? This is bicep left.
Oh.
Come on, everyone. What's the time complexity? If we are finding
log n.
O log n.
Wow.
Okay, let's try to change this to. Look, listen to me. Why this is okay? Because every time we check, this case here includes the equal sign, right? So when it's equal, then we want to move it to the left as much as we can, right? So eventually you will be at the first insertion point, right?
Yeah.
So look, if we try to do this bicep right, everything will be stay the same, but I will just need to change this to bigger than x, and then I will swap it to high equals mid, as this is equal sign, yeah? As low equals mid plus 1, right? So when it's equal, then I want to move this insertion point to the right. So that's why lower. I will move it to upper bound, all right? Towards the right. Every Ryan, are you all right?
Yes.
What's the time complexity for this one as well? Bicep right. Huh? It's the same, yeah? Oh, and log n.
I said O and log n.
Okay.
Yeah, me too.
Okay, so can you explain to me what's the difference between bicep left and bicep right? Come on.
Writing is different. Yeah. And
Sorry. Well, the insertion point is different, right? For the bicep left, let's do.
and this writing is different.
Come on, every line, come on, for the last time, yeah.
And a line just appeared, but not on the left.
1, 2, 2,
And
3.
a list just appeared,
5.
but not on the left.
Okay, so what's the look at this. What's the bicep left 4?
You mean not on the right?
No. Look, this is still bicep left 4. Where is it going to be? Where do you want to put the 4 in?
The second two.
4. I want to put a 4 in this sorted array. So where is it going to be?
There.
Where? Come on.
2, 3,
4.
3, 5.
3, 5. So it's in here. Right? It's in here.
You're pointing to 5.
Yeah, because that's where the 4 is going to be. Okay? And bicep right 4. Is it the same?
1.
Is it the same?
3.
No. Where's the 4 going to be?
1. There.
It's
5.
the same. It's the same. So the only
I said
difference.
5.
The only difference is what? The bicep left, if it's a duplicate element. Right? Look, let's try another one. Bicep left
But there's 2
2.
twos.
2. Okay, where's
But
bicep
there's
left
two
1?
twos.
Okay, yeah. Where's bicep left 2? Which one is going to be? The
The
first
first 2.
First 2, yeah, because
I
because
said 2.
The
The
second.
second 2.
the right, okay, this is before. Where is it?
3.
Yeah, 3. Okay? So why? Because right, all the left will be smaller or equal, right? But for the left, it will be only the left half will be only smaller, right? Because if you put a 2 here, everything up to the 2 should be up to the
It's
2
only 1.
should be, yeah, I know, should be strictly smaller. But for the right, bicep right is strictly or is smaller or equal, right? So it's here, right? That make sense? Yeah.
Why not is 2?
Sorry?
If it can be equal, why isn't it 2?
What do you mean? Which one? The bicep right 2, right?
Yeah.
Bicep right 2, so we put it here because everything up to this point is
But you
strictly.
said it can be
It can be 2, yeah. That's why it's equal to
It can-
2. Yeah. You want to expand these 2?
equal, so but 3 is not equal to 2.
That's why we put it here. We input it here. Alright? Okay.
Because there's already a 2. The same thing again.
Okay. So let's try this. Let's emulate this one a little bit.
Ow!
Low, high, mid.
Ow.
If this point, this mid is bigger than what we are looking for, where is it going to be? The left or right? If the middle one is bigger than the element we're going to look for, so where is this going to be? Left or right? Come on. It's here. What's this? High equals mid. Is it left or right?
High.
High equals mid.
Right. Left.
Not just guessing. Why? Look.
Middle.
This middle thing, a meter bigger than x, right?
Left.
And then high equals mid, so it's left, right?
I said left.
Yeah, left. Okay. As low equals mid high, so you basically moving this low to the middle, yeah?
Arm hurts really
Yeah?
badly.
Okay, that's it for today. Good job. Say bye bye. Bye bye.
My arm hurts.
Bye bye.